You ever wonder how the apps you use every day go from just an idea to this, stable working product on your phone? It's definitely not magic. Today, we're going to pull back the curtain on the master blueprint that software developers use to build pretty much everything. And it's a process designed to keep projects from descending into pure chaos. So let's start with a really big question, one that honestly haunts the entire tech world. Why is it that so many huge, ambitious, sometimes multi-million-dollar software projects just end up failing, or they get canceled halfway through? Well, the answer is actually pretty simple, and our source material uses a great analogy for it. Trying to build a massive software system without a detailed plan is, well, it's like trying to build a skyscraper without a blueprint. You just can't do it. The entire thing is basically doomed from the start. To avoid this disaster, the industry came up with a solution. It's called the Systems Development Lifecycle, or SDLC for short. Now, I want you to think of the SDLC as the master blueprint for building software. It's this formal, structured process that makes sure that every single stage of the project is planned out, controlled, and executed in a totally logical order. The SDLC breaks down this huge, overwhelming task into 7 distinct phases. And we're going to use that skyscraper analogy to walk through each and every one of them, from the very first spark of an idea all the way to what happens years down the line. So the fundamental problem is really clear. If you just dive in and start coding without a plan, you're going to get chaos. Okay, so how do we bring some order to that chaos? Well, it all starts with laying a really solid foundation. Phase 1 is all about project identification. And just like you'd ask, why do we even need a skyscraper right here? This phase is all about asking those really big questions to identify a genuine business need. Is a brand new software system even the right solution? Or is there a simpler way to solve this problem? Once you've confirmed that, yep, we do need to build something, you move into phase 2, initiation and planning. In our skyscraper analogy, this is like securing the plot of land, figuring out the budget, and drawing up a high-level timeline. You define the scope of the project and you create a baseline plan, which almost always includes a cost-benefit analysis to make sure this is actually a good investment. All right, the high-level plan is approved. Now we get to the really fun part, the detailed architectural phase, where the system really starts to take shape on paper. Phase 3, analysis, is a massive reality check. This is where the team does a deep dive, a feasibility study, and they ask 3 absolutely vital questions. First, technical. Do we have the skills and technology to actually build this thing? Second, economic. Looking at the costs and benefits, should we build it? And, maybe the most important question of all, organizational. If we build it, will people actually use it? The big deliverable from this phase is a super important document, the System Requirement Specification, or SRS. This isn't just a list of ideas, it's basically the contract for the project. It spells out in detail exactly what the system has to do, and it becomes the official blueprint that both the developers and the business users agree on. And that blueprint brings us to the next 2 phases, which often happen at the same time: logical and physical design. The best way to think about this is, logical design is the architect's drawing. It focuses on what the system will do from a user's perspective. Physical design, on the other hand, is the engineer's spec sheet. It gets into the nitty-gritty of how it will actually be built, what servers, what databases, what programming languages. It's the what versus the how. So with that super detailed blueprint complete, the hard hats come on and the construction phase can finally get started. Now, a huge part of actually building the software is testing it. Just like a building needs all kinds of inspections, software has to go through these really rigorous checks. First, there's unit testing, which is like inspecting each individual room. Then there's system testing, which checks how all the floors and systems work together. And finally, you have acceptance testing. That's the final walkthrough with the client before they get the keys and officially move in. Speaking of moving in, once the system is built and tested, you have to actually start using it. This is called conversion, and there are basically 4 ways to handle it. You could run the old system and the new system at the same time. That's called parallel, and it's low risk, but really expensive. You could just flip a switch, turn off the old, turn on the new. That's direct cutover, and it's super risky. Or you could be a bit more cautious, maybe with a pilot study in just one department, or a phased approach where you roll it out piece by piece. But here's the thing, the project doesn't just end on move-in day. In fact, in a lot of ways, the work is really just beginning. So we arrive at the final, and usually the longest, phase, operation and maintenance.
This is all the ongoing work, and it comes in 3 flavors. There's corrective maintenance, which is like fixing a leaky pipe, you're just patching bugs. There's adaptive maintenance, which is like renovating the building to meet new city codes. And then there's perfective maintenance, which is like adding a whole new wing because the people living there requested it.
And this brings us to a really key insight about the whole process. Maintenance isn't just some final chore. Anytime you need to make a big change or add a new feature, the team basically runs a mini SDLC all over again. They repeat the cycle of analysis, design, and testing just on a smaller scale. It's a cycle within the larger cycle. And this leads to a pretty profound idea from the source material. This whole life cycle is, well, circular, because eventually any system gets old. It becomes outdated, too expensive to maintain, and its retirement marks the beginning of a brand new SDLC project to build its replacement. Which leaves us with a final question to chew on. If software is constantly being fixed, adapted, enhanced, and eventually replaced, is any of it ever really finished? What the SDLC really shows us is that software isn't some static product you just build and forget. It's a living system constantly evolving to keep up with the world around it.